Okay, let's have a look at how to derive this formula that's given to us in the formula book for sine of a plus b. We're going to start off with this setup. We've got a big black triangle here, which has a hypotenuse of 1, just by convention. You could choose a hypotenuse of r, some random number, but you'll see that in the end you just end up with an r, and it all cancels out. So we might as well just choose 1 to make the calculations easier. And now we're going to write down the two angles. So in this triangle we have angle A, and in this triangle we have angle B. Okay, so we can see that that has an angle of A plus B. And we're just going to now label some of the lengths in these two right angle triangles. Starting off with the top one, because at least we know the hypotenuse of this, we can see that the opposite will be sine A. If you're unsure of why, we can just look at the definition of sine that you have from GCSE. Sine of A is equal to the opposite over the hypotenuse, but our hypotenuse is just 1. So we can see that sine A is the length of the opposite. Similar argument, we can see that the adjacent will just be cos A. Excellent. Now that we've got this blue triangle labelled, we can look at this green triangle with an angle B. We now know the hypotenuse has a length cos A. So again, we can rearrange our SOHCAHTOA formula to see that the opposite will be sine B cos A, and our adjacent will be cos A cos B. Just imagine your cos B equals adjacent over hypotenuse, and your adjacent will be equal to cos B times the hypotenuse cos A, and that is this full length here. Okay, so we wanted to originally find the length of this black line. We've labelled everything we can so far, but all we've got is this bit of the length. We know the first little bit. If we could know the rest of this height, we'd be away. So let's just consider what we have here. We have a nice right angle triangle. We can just extend that line, and we can see that this angle here is angle B. If you're unsure why that is, again, we've got a straight line, 180 degrees. We know one of the angles is 90. This angle here will be 90 minus B. And then we've got that extra angle that perhaps we don't know yet. The 180 will cancel with the 290 degrees, and we're left with 0 equals something minus B. That unknown angle must be B. Okay. So we've got that, and therefore, using your parallel lines rules from GCSE, you can see that that angle is also B. Okay, so let's just work on labelling a few things here. You can see that what we want to know is the length of this line. We know the bottom section, we want to know the top section. We know the hypotenuse of this triangle, so if I could figure out what this adjacent was, I would know the missing length of the line. So again, we can do cos B, because I want the adjacent, times the hypotenuse, sine A, and that will give you that length which we desire there. Okay. You could also view it as being this part of the triangle. Again, same argument, adjacent times the hypotenuse, cos B sine A. Whichever way you see it, we now know the length of this line. Adding those two together, you can see that we do indeed get the formula sine A cos B plus sine B cos A, as required. We just need one more line to actually do the second part of the proof, which is the next formula, cos A plus B is equal to cos A cos B minus sine A sine B. We know that we're looking for this length here in black. We know the length of this big long green line there, cos A cos B. If I take away this green section, I'll be left with the length of that black section. So again, we can find that hypotenuse times sine of B will give me the length of that green section there. And I know I need to subtract that. That's how we can derive the formula for cos of A plus B. We use that diagram. Okay, let's also look at the formula for tan. Now that we know the formula for sine A plus B and cos A plus B, we can use those formulae. Tan of A plus B is equal to sine of A plus B all over cos A plus B. Using the expansions we've just discovered, we get sine A cos B plus sine B cos A over cos A cos B minus sine A sine B. Okay, now one thing you'll find in trig, sometimes you have to think about what you're aiming for in order to know a next step. We want to arrive at the formula tan A plus tan B over 1 minus tan A tan B. So we want all of this to be written in terms of tan only. Well, if I've got sines on the top, I know that I can turn a sine A into a tan A by dividing through by cos A. Tan is sine over cos. Similarly for B. So what I'm going to do is, I'm going to divide the top of this fraction and the bottom of this fraction by cos B cos A. So here I'm going to have sine A cos B divided by cos A cos B plus sine B cos A over cos A cos B, and the same on the denominator. Remember, I'm not changing a fraction if I multiply top and bottom by exactly the same thing. Okay, so we've got that, and now we'll notice the cancellations. Cos B divided by cos B, they will cancel out. Sin A over cos A, that is the tan A I wanted. Similar here, I've got cos A over cos A, I'm left with sin B over cos B. Exactly what I want. I can see that's going to give me my tan. Cos A over cos A, cos B over cos B, that cancels down to 1. Sin A over cos B. Sign error there, I wrote in the wrong thing. Tan A and sin B over cos B, that will give me a tan B. Okay, I've cancelled it down to exactly what I wanted. I've proven that formula. The key is to this one is keeping one eye on what you're aiming for. If you're aiming for tan, you know that that's sine over cos. So tan A, you know you need to divide your sine A by a cos A. As soon as I do it to one term on the numerator, I must do it to each term on the numerator and the denominator so that I don't actually change what my fraction is worth. And that's how we can derive our formulae that are in the formula book.